Good morning, folks. Thanks for coming in. How are you all?
Good.
I'm now back, as you can hopefully see. This is me to the end of the module. It's only about 5 lectures worth, I think. 5-ish. We'll see how we get on, see how we go. And I'm just going to finish off basically by talking about cluster computing in general, grid processing in general, because you've been looking pretty much at Hadoop and a little bit of Spark, and they're very much focused on a particular type of processing model, which is heavily data-based and data-oriented with large data sets. And I would like to just give you the bigger picture. Hopefully that's of interest. Because quite a lot of the time you're not dealing with vast amounts of data, you're actually dealing with a relatively small amount of data, maybe even just 10 or 100 megabytes, nothing too big. But what you are dealing with is a large computation job. We handle that differently to the way you do it. So that's what I'm going to talk about. I'm going to show you it, well, I'm going to talk about the principles, and I'm also going to show you it using our in-house Condor system, which is a sort of process scavenging cluster system. But the idea is that I'm going to try and put across match to other dedicated high performance computing environments. So for example, there's one at Strathclyde we have access to, there's another one at Edinburgh that we have access to. It's the same idea. We just have to have one here locally that we find quite useful. If you get the ideas for this, it's very easy to migrate to the other ones. So the idea being that in your job you need to use some high performance computing, you'll be pretty familiar with the principles. That's my goal. So hopefully I can sell you on that.
Is that, dare I ask, is that of interest?
I hope so. Given the module, so pretty much just said what I'm about to say. What we're not going to look at as far as the cluster processing principles go, and this is a good thing, I think you'll hopefully find, is inter-process communication. Has any of you done distributed systems with communication message passing before? Deadlock? Yeah?
You have theoretical idea.
Theoretically, you're not done it for real. Well, you will be doing this for real. But hopefully you can remember that if you start to do inter-process communication where processes are waiting on other processes, it can very quickly go pear-shaped. Yeah? We're not doing that, so that's good. This is actually relatively easy to massively parallelize because we stick to certain principles.
Okay. Oh, and as usual, please just ask away if you've got any queries that are vaguely related to what I'm talking about.
You can ask me Java-related ones as well if you like, I think. I'm going to go through the principles here, and then I'm going to start showing you examples, starting from the really basic hello world, and work my way up. And I'm hoping that the later examples will be quite useful for your assignment, because I'm going to be doing some sort of, I'm going to do an equivalent to word counts, for example, where I use hash maps. I think you're using hash maps for your assignment. So I've got some code that you'll get that you'll be able to see how I use hash maps. And from memory from previous years, folk have gone, oh, I'll be taking that, thank you very much. It's been quite relevant. So your assignment's still a couple of weeks to run, isn't it? 2 or 3 weeks to run. So hopefully I'll get to that in time. Before I forget as well, there's lectures today. There'll be 2 lectures on Monday. So there will be a 5 o'clock next Monday. There'll be a lecture on the Thursday and the following Monday, and we'll see where we get to. I will try and make sure you don't have a 5 o'clock on the final one, but we'll see where we get to sometimes. Right, so what are we looking at? We're going to start looking at jobs where we're not trying, we haven't got a database that's so vast that effectively the data is already been distributed and the processing effort is moved where the data is, which is, that's Hadoop, effectively. We're trying to take a situation where actually, no, the biggest problem we have is we have a large processing job and we need to distribute the processing effort, and the data is going to have to move out to the processors. So in this kind of environment, the data is not sitting there waiting for you, it hasn't been partitioned. With the Condor environment, the data is moved to where your processor is, it's copied. You do get some environments, for example, with the supercomputing facility at Strathclyde, there is a network file system. and it is a very high performance network file system.
NFS.
It's, I can't remember the name of it right now, but it is very, very fast. It was on, I think it cost almost as much as all the nodes. So at Strathclyde, they've got about 3,500 nodes. These are cores, by the way, so these aren't 3,500 single computers, it's cores. So one computer can have multiple cores. But the networking costs almost as much as all the cores together. But there can be issues as that as well. If you imagine if you're reading and writing from a network file store, and you've got multiple jobs writing to the network file store, what headache can you get?
Attention.
Well, you get that, and also if you've not thought things through about your multiple parallel jobs, yes, you get this combo as well.
Inter-process communication or inter-thread communication.
You won't have to do that with what we're doing. I was thinking simply overwriting what you've already written. You'll be very careful about what the job's producing and then managing the names of all the jobs. The other thing I'd like to think about is, I mean, maybe you've already thought about this yourself, is why would I bother doing this? Why don't I just run this all on my own PC? And there is an element of that. The jobs you're doing have to be big enough to be worth the trouble. Because certainly in my experience, I mean, I use Condor to do a lot of evolution computation tasks. And I do ask myself sometimes, how much work is going to be involved? Because I often spend more effort structuring my code, structuring the problem and getting it all configured. I have more time doing that than I do actually writing the code. And if I'm not going to run it very often, it's not worth it. You know, if it's a case of running it overnight and I'm still going to get a result in the morning, then I'll probably go with it. But if it's a case that it would take you hundreds of hours of CPU time, then it is worth it, and that is the situation I find myself in. So you've got to ask yourself how much effort, and I'm going to come back to this as far as programming languages go. And sometimes you don't know. So you're pretty familiar with MapReduce now. I take it as a pattern, as a design pattern. It's a very common one, and it's still one that we're going to do. Not necessarily with data, but with the processing effort. You take some problem, you partition it out, you do some computation, and then you reduce it back in, you condense it back in, kind of distill what you're looking for. Yeah? Yes?
Do we have one question, which is very good feature for distributed environment cluster computing.
Yes.
But is it possible that, you know, within a single computer having multiple cores and multiple processors to distribute job using MapReduce within a single computer? If it does have multiple processors.
If it has multiple cores, then yes. I'm going to come to describe Condor shortly. What's rather nice about Condor, actually in all these grid processing systems, the one that Strathclyde is the same, is you don't have to care. You don't have to think. I mean, if you're doing this, if you're writing C code on a specific PC and you want to use the multiple cores, and you're not using some cluster architecture, what have you got to do? You've really got to write your code in a multi-threaded way, don't you? You have to say, right, let's just put that on thread 1, that on thread 2, make sure that gets a core of its own, don't create any more threads than you have cores. You've got to manage that process. Has anybody tried to do that sort of stuff before? It's pretty tedious, isn't it? You have to be really quite careful about what you're doing.
Usually doesn't work.
That's extremely obvious. Exactly. Or you think it's working, but when you look behind the scenes, it hasn't done what you thought. Because you don't have complete control over it, do you? Well, these systems, these high-performance computing systems, have this distributed part at its core, and they take care of that for you. They literally will put it on a single core and give it some disk space associated with it, and you don't have to worry about it. As far as you're concerned, you have a job, you create it, you say, you just take it away, make it happen.
Kind of a multi-threading should always not be.
Yeah.
Sounds okay. You can have all that stuff.
It's really hard work, and it's so easy to get it wrong. And it's so easy to get it to lock up. Whereas this sort of system, it does it for you. It's really nice. I'm going to take the giant thing. Well, you can tell me when I've shown you how it works if you think this is a nice way of doing it. It's also extremely flexible. Right. I'll come back to that sort of GPU bit in a minute. So, what I'm going to look at, I'm going to start off with some really simple ideas. So I'll start with word counts that you're familiar with, not because you'd ever use these architectures to do word counts, although one of the things I will do is just say, right, let's take the word counts and then let's look at DNA analysis. it's just counting words or patterns in pattern analysis. So actually it does turn out to be quite useful. I'll look at some of the issues about when you can and can't split a task up. And then I'm going to sort of move to more and more complicated examples. So will you humanly want to do the simple ones? Or is it more a case of humanly want to do more complicated ones? But this is the idea. I want you to, I don't know about you, but when I'm trying to learn something, I like a really simple example to start with, and then just step it up and step it up. So that's the approach I'm going to take. I'll start off by showing you how to do Condor jobs in Java, C, Python, just so you can see the similarities between them. They're actually very, very, very similar. And then we'll move on to actually a problem that I've been dealing with, which is a sort of variant of traveling salesman problem, and show you how I've actually used it. And it's the reason I'm doing this part of the module anyway, because this is what I do.
Travel with you?
Thankfully not. People are forced to take the routes that I come up with. Bizarrely, I'm looking at, well, it started off as travelling midwives, believe it or not, and now we're considering travelling dementia carers, because it turns out to be quite a hard problem. I'll say to that, otherwise I'll just go a tangent. It's one of those things that looks quite innocent, and then the deeper you look, the worse it gets. So, we have some processing job. We have to consider how we're going to partition it up. How many pieces we can break it into. I would suggest ideally you want lots and lots of small jobs. The downside of those is you end up with lots and lots of little files that you then have to stick back together again. But generally, you're a lot better off having a large number of very small jobs, because you generally have a very large number of nodes to run on. If you have a small number of large jobs, then you run the job itself can take days to run. And in a sense, the size of the job usually determines the run length of it. If you can split it up, what you have are literally, in the case of Strathclyde, thousands of nodes. If you do, say, 1,000 nodes doing 10 minutes of work, and you've got 10,000 minutes worth of work versus 10 jobs doing 1,000 minutes of work, you've got to wait 1,000 minutes for that to finish. Although, there's also the risk with systems like Condor that actually your job can get bumped. Condor's a process scavenger. It's running on machines that aren't busy. Well, it's a combination of both, but the lab machines you're using in 4x5, for example, are all Condor nodes. The minute you log off, they pop up and say, I'm free to do some work. But if somebody comes along and logs in, that job gets kicked. So that job's been running for 3 days. That's a bit depressing. We have a bunch of Linux nodes that are dedicated Condor nodes. Nobody logs into them. They keep running. But they're even nicer, because even if somebody does interrupt them, the process image gets copied to another node and just carries on where it left off. Unfortunately, Windows won't allow us to do that. So, but we do have a good cluster of Linux nodes, which are always contended, because everybody wants those ones and not the Windows nodes.
So we can transfer session even if we log off to another system.
It does it for you. You don't have to work. You set the job going, you can log off and go and have a coffee or go home. It keeps going. You don't manage any of it. It all just happens. If the job gets kicked, it gets restarted on another machine. You don't have to worry about it. They're great. It really is good. So I'll come back to that. Now, as I said, Condor's a scavenger, and it suits our environment. Strathclyde's dedicated. Its whole job, it's called Archie West. Its whole job is to do cluster programming, but it's shared across 5 Scottish universities. So 3,500 nodes sounds like a lot, but that's all departments in all those universities. And sometimes we've got priority access. So even though you think you've got thousands of nodes at your disposal, you often don't. Whereas here, our nodes, 700 of them, they belong to us. So, and you're going to be using them. Oh, that is actually one thing I should say. You should now have access to this Condor cluster that's available on Pound. I've put the practical sheet up that you will be doing, which is basically the examples I'm going to be working through. Practical's not till the 27th, I think. Next Tuesday you're going away somewhere? Yeah. but the following Tuesdays are actually in the practice list. But I'll put it up anyway if you want to muck about with it. The only thing, it'll be D7 Condor. Is a practice sheet. And it basically just walks through what I'm doing in these lectures and sort of towards the end when I say we'll do something different. But Condor is a real research tool. We do use it. In fact, I think right now Sandy Brownlee is busy using it to do some work for a research paper. So please don't go crazy with it. It's very easy to run thousands of jobs. You just change one number. So it's okay if you want to try things out and say 20 or 30, but please don't go, hey, why happens if I put 10,000 in here? Sandy will cry because he's trying to get a deadline. So please respect it. We're allowing you to use our research kit, but it really isn't used to do work. So it's not a purely lab environment. I'm sure you're all fine, but I thought I just want to put that out there. Yeah, no crypto mining, please. Just in case.
We will notice. Yes, because everybody can see what everybody else is doing, by the way. You can see all the other jobs that are queued or running. So, and I'm often just having a little look, so we'll know. Right. So how does it work? Well, you log in to a... let me just go to a diagram, actually. You log in
to a submission host, which is pound 0 is its alias. And this is the only contact you really have in theory with the cluster. You log into the submission host, and on that submission host you submit a job. The submission host is in contact with the whole cluster manager and finds out what nodes are available. You've got a whole bunch of nodes that are running away. So these are the lab machines, the Unix cluster. When they fire up, they contact the central manager and they say, here I am, I'm available to do the work, let me know. So the submission host negotiates with the central manager, says, I've got a job, and then it tries to match the job that it's been given with the capabilities of the node. So for example, sometimes you say, I only want this to run on the Linux nodes. It'll find all the Linux nodes. And then your job is sent off to each of these nodes. Not that you have to worry about it, you just submit a job here and off it goes. However, when it goes off to these nodes, it will have a flat file space made for it, and all the files that you noted in your submission job will get copied to that directory. You will not be able to refer to subdirectories. You will not be able to write out the subdirectories. You basically just get a directory that you're running in, and everything has to be there. Yeah. So that is a bit of a constraint at times. We'll go into how exactly you set this up in a bit.
One question. When these jobs are submitted by the central manager to one computer, then each computer does run its own operating system, and the operating system does have a mechanism to assign priority to each process, because in multi-programming, each process does have a priority number.
Yeah.
That is assigned to a local operating system on local machine. So when
Yes.
this remote job is received by a computer, then how its priority is assigned? Is it assigned by the same local operating system on the machine, or it already gets priority?
What's running on each of these machines is a Condor client, and then it'll be assigned that. I think it has a fairly low priority, to be honest, because it gets bumped the minute you move the mouse or tap the keyboard, it's gone, which is not very priority at all. But it's the priority of that client, and it's installed as a system level service. It's not a user level service, so it is a fairly low priority. Yeah, but you don't have to worry about any of that. It just goes out there. You can download Condor yourself if you ever abuse and you've got 3 days that you'd like to waste. It's one of those things that's an absolute pain to get going, and then once it's going, it's fine. It goes to salt sometimes. I'm kidding, it shouldn't be 3 days, but it's a lot better than it used to be. But you can just download it and install the client and the manager and so on. And there's a lovely configuration file you go through trying to...
Can we access it from our system from here?
You will be able to remote log into this. It's if you use Secure Shell SSH, if you've got SSH available, then yes, you can remote log into it. It'll point at your file store here though, so you'll need to be able to content in your file store that you're using here to get material into. Unless you can do secure copy, if you can use SSH, then you can use SCP to do the same thing and copy stuff into the Commodore directories. But absolutely, that's another thing. I mean, I often work from home, and it's very nice. I can just remote log in and just send stuff there, get the job running, go off, make a cup of tea. And come back. It's very, very good for that. These systems are designed to do that. I mean, Strathclyde system, we don't go to Strathclyde to use it. It's all very much remote logging. Yes. These are all good questions. You okay with that? Yes, Principal?
This is me just actually talking through what I said. I don't think I need to repeat that. So,
Commodore's universes. It only has two universes, effectively. One is vanilla and one is Java. The idea of the universe is what environment am I running in? What kind of vanilla is you're just running in the environment of the machine itself. You have to comply with that machine's OS picture, as it were. So if it's a Windows machine, you'll have to build an executable that runs on that Windows machine specifically. So if you've done a Linux build and you try and send it to the wrong OS, it won't work. Whereas Java, as you know, build one to run anywhere. It's basically saying this machine has the Java VM on it that it will support. So you must make sure that you match the executable you'd like to use with the environment it's going to run on. So this is where, for me, Java comes in really, really handy, because I develop on my Mac, which is there, and I submit it to the Commodore system, which is running Linux and Windows. But it doesn't matter. It just runs on all of the nodes. So developing Java means I have access to all 700 odd available nodes. Just trying to fix Java a little bit here. It really, really helps me a lot in this environment. And thankfully, Java is now a lot quicker than it used to be. The modern Java compiler compiler plus the virtual machine itself. It's really the virtual machine that's made the difference. It's so much faster than it used to be. What's particularly nice is the fact that it actually does just-in-time compilation of the actual Java bytecode into local machine code if you keep running the same process or methods over and over again. So you effectively, after a while, start to run things at sort of on par with how a fast C program will run, because you've actually got local machine code for the machine it's running on. And it's particularly suitable for this environment because you are running a process over and over and over again. Yeah. The problem with C++ is much faster, or a good bit faster anyway, but I have to start making executables for each one. I can't just take the same Commodore job and say, just send it out please, make it run. I actually have to say, right, here's one Commodore submission job for the C bit, so for the Windows machines of this particular OS, and here's another one for the Linux machines, and here's one for Mac so I have to do it, and that's just a pain. It may be worth it, depends what you're doing. As a matter of interest, any idea how, I've got a draft next, those of you who my lecture notes, of performance difference between Java and C++. So how much quicker do you think C++ is these days than Java? 4 times? 4 times? It does. Oh yeah, I mean, just an order of magnitude. I mean, you're actually pretty close. So what I've got here is, there's a benchmark website which is rather nice. They've got a number of benchmark problems. So these are a bunch of different benchmark problems. And this is the execution speed of a C++ program executing that problem versus a Java program executing that problem. So here, that's it nearly 3 times faster, as it executed in a third of the time that the Java one did. A lot of them it's about 50% faster. Memory usage of C was generally, this is memory usage for the same benchmark problems, and it's a bit more efficient. It's hard to beat C++, particularly C if you really go for it. but you have to put more effort into writing that code, so think about it. And then code length for the same benchmark problems, sometimes C is shorter, sometimes it's longer. So there's not much of a difference. So that's one choice you have. Another choice you might say is, well, it's taking me ages to write this. I could do this in Python. And Python in theory, well not really in practice, I suppose, has the same advantage as Java, where you can write a Python program on this, on my Mac, and then distribute it out to any machine and you know that has a Python interpreter on it that matches the environment that you're I can probably build Python programs on my Mac that will run on the Linux nodes because the file structure is very, very similar, the libraries are very similar. It's a little bit more tenuous if I try and put them on the Windows environment, but I might get away with it. However, Python's a good bit slower than Java or C++. So you have to kind of balance how much effort you'll save by writing in Python, if that's what you're familiar with, and how quickly you get it working yourself, versus how many times you're then going to submit this job and run this job. If it's a one-off and you've got a bit of spare processing power, then you probably want to write it in Python. If it's something that you're going to be doing every week for a couple of years, and you're going to do it, you might want to use a couple of thousand CPU hours, and then you might start to think about it. But it's very, very good as a prototyping. To me, Python works fantastically as a prototype language. You're just trying an idea out and getting to work and see if it's going to do what you want. But there's a kicker with speed. Now, it is true that if you're doing mostly matrix manipulation in Python, there are C libraries that are reasonably quick. And you basically get the situation where actually what's running most of the time is the C library and not the Python code, because the Python code is interpreted, but that's not always the case. You get a bit of a loss of overhead. But just as a matter of curiosity, have you got any ideas how much slower Python is than Java on that same 10? Yeah? 4?
Magnitude 10.
10.
Magnitude 10.
Got any bids on 10? 10. Anybody want to? Anybody want to go for 20?
Yeah, 20.
20. 20. 30? Can I take this to 30? Can I get 30?
35.
35. 50. Right. Yeah, well, think more like 100 in many cases. And this is compared with Java. So you then have to multiply that by at least 2 to compare it with C++. So a C program, C++ program, in the same benchmark cases, is likely to run 150 to 200 times quicker than your Python program. And these are the same benchmark problems. That's a heck of a kick. It's particularly bad news if you're using a cluster facility and you're paying for it. If you said to your boss, well, I'm going to use Python, there's going to be a more, it's going to cost 200 times more than it would have done if I'd written it in C, but don't you worry about that. See where I'm coming from? A lot of the time we can get away with it, but the minute you're actually paying for process time, and you pay for process time per CPU hour, it starts to hurt. So bear that in mind. I'm not saying don't use Python, but beware what you're doing. A lot of the time, actually, where this becomes a sticking point is turnaround time. Even if you've got, we've got free use of Congo clusters, so that's not an issue. But if it's going to take 200 times longer, if for example I'm running a job and I've written it in C++, and or if I've written in C++, and taken an hour to run, or let's say it takes 8 hours to run, and I'm trying to work my way through a problem and see where things are going. So what I'm going to do at the end of the day, at 5 o'clock, I'll submit the job, and I'll go home for the night, so that when I come back in the morning, I can have a look at the result. What's the problem with Python? You must have gone on holiday for quite a while. Actually, 200 times a day. That's quite a while. Yeah, I should have said 300, but maybe my days a lot easier. You get the idea, you suddenly lost that turnaround time. I actually saw this in the division. There was one of the maths lecturers who was doing some research, and it was taking a day for the Python code. Yes? Yeah, no, they're right. And as you say, if you can link it and run it, most of it in C, then you'll get a significant boost, but it won't take you to the levels of Java or Python or C++. Certainly not the levels of C and C++. You might start to get close to Java. The problem with Python is the way the language works. Its language structures sort of don't allow a lot of optimization to be done. You're getting your benefit not from Python, but from C. And linking through C and working through C. Python's so flexible that it becomes very, very hard to optimize it down because it's in principle interpreted. I have an example of some code that a student ran last year, which I'll see if I can dig it out. He was gobsmacked because he wrote some code in Python to do some calculations using least squares, and then he wrote it in Java out of curiosity. And the difference was quite marked. Couldn't believe it. He wrote both bits to be as efficient as he could. What I'm trying to get over here is just be careful about the compromises you make. I mean, I like using Python to get stuff done and do the sort of data analysis and pull things together. It's great for that. Boy, is that stuff tedious in Java. But I guess what I'm trying to say is use the language for the problem. Think about what you're doing. I mean, the reason people love Python is this bit. Python code is very succinct. Is that fair to say? This is you here effectively having to type stuff up. It is definitely quite tightly focused. So, just a point to make: pick the job. There is one step beyond this. That's madness, isn't it? Which is you can go the whole hog. We've got. You've got your so running things like single CPU, you've got distributed processing, you've got your Hadoop set up. If the job warrants it, the next step is actually to do GPU programming, where you have to write things in CUDA, and you have to really specifically focus your processing job to that environment. Modern GPUs are just phenomenal number crunchers, as you're probably well aware with Bitcoin, and if anybody's into gaming, they're probably furious about this right now because modern GPUs have become so expensive. Gaming GPUs you can't buy them at retail prices anymore, so all crypto miners are buying them up. They're basically massive matrix multipliers, massively parallel matrix multipliers. So you can use these environments to run your jobs, but you have to really turn the job into a pattern structure that fits what the GPU is good at. And it takes a lot of effort, and you only do it if you're going to be doing this job over and over and over again, and it's worth your many, many hours to turn it into a CUDA job. We're not going to do that because we'll have to teach people to learn C, and it's not something you do very often. Any questions? I've got time enough to check some. Right, so what I'm going to move on to next is actually showing you how to do this. So we're going to start off with some simple examples, and everything we're going to be doing in the long run will be using Java and jars. Basically, you take a piece of Java code, bundle up all Java content, and export things as jar. If you're using Eclipse, it's very easy, and that's what you submit on Condor Notes. So I'm going to start the next set of lecture slides, if that's okay, because I'd like to be showing you using Condor. The more I get done now, the sooner we'll finish at the end. So let's go to how it all actually works. So I'm going to start off with Hello World examples. You're all familiar with the idea of Hello World example, which is let's just get the simplest piece of code we can that does something in that language, even if it doesn't make it useful, just so we know it's worked. So this code shouldn't come as a surprise to anybody. Perfectly happy with that? Java's version of Hello World. We take that, we build this in Eclipse, it takes ages, and then we export it as a jar, and it's a jar that we're going to send off to the Condors system. So, right, so we have our code bundled up in a jar with all the classes in it. Jars are really nice because they have, you can have a complex class hierarchy with all the various class files, and they all just get bundled together with any resources they needed, and off they go. And then what we do is we create a text file specifying the submission job for Condor. So here it is, it's just a text file, there's nothing clever about it, there's no special tool. So I'm going to create a text file called hello.txt, and this is what we put in it. Has that been like that for ages and you've all just been very patient? Sorry, if it does... No, that's not good. How about here? That's got to be better over there anyway. First off, we're going to be using a Java program. So we say universe equals Java. So this is a Condor submission. It's just a bunch of configuration assignments. We tell it that the executable will be this jar. The arguments will be hello. So arguments are how do you run this from command line. It's basically saying run the class hello. It's saying here's a list of jar files. So you can have a separate list of jar files that you need to run it. So perhaps your jar file needs a whole lot of jar libraries to go with it. So you will specify them there. And then you can give it 3 output files. One is a log file, which is where the whole submission and running and completion log information gets dumped. It's just a text file. If anything goes wrong, so anything going to standard output, that would go, standard error would go into hello.vir. It can be hello.vir.text if you want. I've just used these as a mention. And finally, anything that goes to standard output will go to that file there. One of the things we tend to do with Condor jobs is you can write stuff to files, but often it's nicer if you just write stuff to standard output. Your system.output.println. Because we can collect it all up here, and we can collect it all up as different named files, and then glue them all back together again. And then this Q1 is just literally run that job once. That's it. It's a Condor submission file. That's not so bad. Remember I was saying earlier on, please respect that this is a research tool, because you can put Q10,000 if you really want. That's as easy as it is to submit 10,000 jobs. It's rather lovely, isn't it? In fact, what you can do is you can put a whole load of information, you can repeat this information, change some of this and then queue another 10, and then change it again, you go queue another 10. So this file can queue many, many jobs with slight changes in the parameters, for example. This is how I use it. I change what the arguments are, and then I queue another 10, and then change the arguments again and queue another 10. And the one file will maybe submit 100 different jobs. Okay, so far? Does it look easy? Sorry?
So far, so good.
So far, so good. You're very wary. Yeah?
Must maybe submission always be a text file.
The format should be, it's just a text file. You can call it whatever you like. Quite often we call them .subs, but then I got annoyed because then when you double click on it, Windows doesn't know what file is. So it's just a text file. It's entirely up to you what you call it. Condor doesn't care. Whatever you find easiest. But it is a text file. It's just a standard text. You don't submit a Word document or anything like that. It's not going to work. Just raw text.
Do all the jobs have to be received directly?
Not quite, but they can, yes. I'll come to that.
Okay. They just didn't specify directories there, that's quite unusual.
Yes. I will. It used to be you couldn't at all, which is a pain. It used to be you had, and you couldn't use wildcards either. So you had to literally specify every single thing that you wanted. Thankfully, we're not there now. There's a slight improvement. Yeah, I'll come back to that one. Basically, you can give a directory, say everything in here, copy it. So I've gone through that, and this is how we submit it.
we make sure that this file and the jar file associated with it are in a directory that's visible on the submission machine on pound, and then you go Condor submit hello result. So I should do that, shouldn't I? Just to prove the point. So let's have a look. Am I still here? So I logged in. This machine's got SSH built in on the command line, thankfully. Not all of them do. So here I am actually on the Condor submission node. I've got a directory called Condor, so I'll go into Condor. And then in here, actually I've got a D7 directory. And let's go into hello, which is another directory. Oh, and then I've got hello. Now I've got 3 different versions of this for your entertainment. So I will go to hello.j, because that was the Java one. Right, here we go, finally. I have a directory called hello.j. I've got my jar file, and I can see... By the way, this is running Unix, well, sorry, Linux. This is a Linux machine, so you'll need to use Linux commands in here, not DOS commands. I think I'll give you a few of them in the practical sheet just to get you going. So I'm just going to have a quick look. That is the content of that submission file. There's one thing I've tweaked, which is instead of giving a proper file name here, I've put $brackets process. This is a macro substitution, so all it's going to do is replace what is here as $brackets process with the process number that actually ran. This is particularly useful if I want to run 100 jobs. I don't want them all coming back as hello out.txt. I want each of them to be numbered by the job number that they ran. So this will substitute this text here with whatever one it was. Well, I'll show you that in a minute. But for now, I'm just going to queue one job. So fingers crossed. Sandy was rather hogging this earlier on this morning. So I go condor_submit and then sub. By the way, in Linux, Unix, you can partially type something. You can do it in DOS actually. Partially type something and hit the tab key, and it will try and auto-complete, or at least auto-complete as much as it can. That's very handy. So here we go. Right, it says it's submitted it. I can now go condor_q, and I can type my initials. So you type yours, and I can find out jobs associated with me. Oh, they're not there. Why are they not there? Because it was so much effort. It's finished. Sometimes they are there. It's something to be wary of. A job can sit there for a couple of minutes and do nothing before it finally gets scheduled. So we can look at hello.log. Is probably the first one. So that just tells me when it was submitted, when it executed, and what happened. Not much happened. It didn't. Yeah, not a great deal of effort was involved in that. But it was all happy. Everything worked. So if things aren't working out right, you can look in there to say, well, what happened to it? Where did it go? What did it get suspended? Sometimes you can see it gets submitted and then just go to being held because things weren't configured right. Hopefully, hello.log. Sorry, hello.er will hopefully be empty in this case. Yep, nothing in that. And obviously, the bit we're really excited about is the contents of hello-0. Oh, no. There we go. The contents. That's the output of our job. Now, we could be, a bit radical. Right, what I want to do, I want to edit sub. Right. So, if I now want to run, I was going to ask you for a number, but I'm not going to. I've decided 10 will be sufficient. Just in case I'm just too used to the undergraduates. Any opportunity I give them to cause things to go wrong, they love it. They just go straight for it. So I'll write that out. So now I'm going to do that same submission job again. I'll get there eventually. And that should run 10 jobs, where the output should be numbered hello 0 to 9.txt. Right, if I'm quick enough. Got them. There they are. So they're actually idle at the moment. They haven't run. This is the I, and this is them idle. Uh-oh, I've just submitted another. So I meant to do that. okay, it's still managed to deal with the first batch, and then I'll look at the queue again, and now it's all done. And actually what I'll have done, the second batch will overwrite the file names of the first batch, because I didn't change anything there. But we ran 20 jobs, and the first 10 got overwritten by me accidentally running the second 10, because they've got all the same file names. But if I have a look now, we have now got, really exciting, hello 0 all the way up to hello 9.txt, telling me that that's the output of job. Thanks. Can you see now what that dollar process thing has done? Yep.
Why would we run the same job many times?
We certainly wouldn't run this 20 times. That's an excellent question. I'm just showing you the mechanics of this. There's no real gain to be had making lots of files with hello.txt in them. But I will get to examples where, well, the way maybe this is a good point to sort of sum up, and we'll leave it here for today. And then next week I'll have a look at showing you this with C and Python and slight differences you do. The way I use it is I use genetic algorithms, evolutionary algorithms to try and solve problems. But these are stochastic processes that have an awful lot of randomness in them. And it's really dangerous from a research point of view to run something once, get a good result, and go, yes, solved it. Yeah? Because you can run it again and get an awful result. What you have to do is run it a couple of hundred times at least, and then look at the distribution, look at the spread, and say, how consistent is this? If I get a massive spread, it's telling me that my algorithm that I thought was fantastic is very susceptible to noise and not reliable at all. And that's why I want to see what that variance is. So that's a very common reason we use it in the division, but there are plenty of other examples. Does that help? Yeah. It's very necessary. If we try and submit to a journal the result of one run, they'll just laugh at us. And you could read, well, I guess. And the same if I get paid to review, I think, what? You're building all your future hopes on this one result. It's extremely important to show that this is robust across many, many different cases. And that's what I do in the long run. I will finally sum up at the end of my last lecture showing you what I've used it for. Yep.
The process ID also, job ID or process ID, is that guaranteed to be 0 to 9 for your?
Yes, it is.
You can actually, yes, you can see here there's actually two process, that's the job 7 for example of process 62599. You can actually remove jobs, so I could have, if I'd got there fast enough, I could have gone condor RM and I could give the specific 62599.7 to get rid of that one, or I could go 6259 to get rid of the whole job.
If you want to process the files afterwards, you're guaranteed to get 0 to 9. So
You are, yes. But if you do like I did and run it twice over, then you're overwritten your first batch. But absolutely, this is often slightly the headache, is making sure you get unique output. The one with using standard out and using dollar process is one way to do it. The other way is to pass in a command line argument when you run the job in the first place, so your code knows what its job is. And a combination of the two can usually allow you to have a bespoke file name for each particular thing that's happening. And that's the way I use it. I pass in as a command line argument to the job, saying your job is to do this, and when you do this 100 times, and they all get labelled by process number, and then I give another batch of jobs, and the command line argument is slightly different, and I can use that to create a slightly different file. I'll show you all of this later on, but yes. Managing all these files that you're producing is sometimes a bit fiddly.
Which is the other something from the other file.
In the
other file, you say you have that's fine.
You can, the stuff that's going to standard output, you're limited to what you can do in the Condor submission, but you can also get, as I said, you can get your Condor job to write files itself, and they will get scooped up and sent back. And you can pass the process number in as a command line argument itself.
For instance, Java, can you work out who you are?
Yes. By doing that, because you can pass that command, you can pass dollar process as a command line argument, and it will be 0 to whatever. You've got that, and you can provide any other arguments you want. So it's all doable to control. I'm kind of pleased to see that you're picking up where you actually end up having to be careful about how you manage it and what results you get back. That's the thing that trips me up. I'm thinking, well, what is that part of 100 files telling me? So anyway, thanks. I hope that was of some interest, and I'll carry on Monday with more demos.
That's also the